So in this section, we are going to really talk about a lot of the theory that we're going to use for the rest of the course. This is a section where it's definitely not easy to teach. You're going to want to go through and read the textbook. We're going to talk about some of the examples in the textbook, some of the principles, like the superposition principle, that we need and we're going to end up using for the rest of the course. So let's get started. So we're going to start out by just talking about what an nth order initial value problem is. So here's our initial value problem. Okay, it's nth order because we have an nth derivative here, and that's the highest order derivative we have. Notice we have a set of initial conditions here, and they are initial conditions. They're all imposed at x naught. So that's the x value that we're plugging into each one. So remember, when you have an initial value problem, suppose we have a first order initial value problem, then we know we've got to have one initial condition to solve for that constant. If we have a second order initial value problem, then we have to have two initial conditions to solve for both of the constants. So then if we have an nth order initial value problem, then we have to have n different initial conditions to solve for all of the different constants that we would have that result from the integration. So let's talk about uniqueness. Theorem 411 states that if we have an nth order initial value problem, and we're going to let all of those coefficients here, along with that g of x, be continuous on some interval, and we're going to let x naught not be equal to 0 for every x in this interval. We're going to use that initial value. That initial value has to be on this interval. Then there is going to be a solution for this initial value problem that will be unique and will exist on this interval. So let's kind of break that down. So I'm going to go back up here to my differential equation. So what we're saying is, here's our constants. And remember, now we're thinking about constants not necessarily as numbers, but they could be, not constants, coefficients. Coefficients aren't necessarily numbers. They can be functions in terms of x. And then we have the function in terms of x over here, which is what helps make this linear. All of these are in terms of just x, or they could just be a number. So we want all of those to be continuous on some specific interval, and we're going to be very generic and just call it interval I. We also don't want an of x to be 0 for every x in this interval. Actually, we don't want this to be 0 for any x in this interval. If this is completely 0 to begin with, this is no longer an nth order, because this would be 0 times that derivative, which means that term would go away. So we don't want it to be 0, just 0. We want to keep it in nth order, not in n minus first order differential equation. But we don't want it to be 0 for any x in this interval. So as long as we're meeting all of that criteria, we have continuous functions on some interval, we're not 0 in that interval, and we have an initial condition that exists on this interval, then we can guarantee that the solution for this differential equation is going to not only exist, but it's going to be unique. Unique means there's only one solution that's going to satisfy all of that criteria. So let's look at an example. Here's an initial value problem. This is a third order differential equation. We have constant coefficients here. Notice our a sub n, in this case it would be a sub 3, is the constant 3, which is never 0. Initial conditions are imposed at 1. So this guy is actually continuous from negative infinity to infinity. No issues there. We could think about these constants in terms of functions. So we could think about this like the line y equals 3. Y equals 3 is a continuous function. Y equals 5 is a continuous function. Y equals negative 1 is a continuous function. And y equals 0 is a continuous function. So there's the interval I that we could talk about here. initial conditions are defined on that interval. X equals 1 exists in that interval from negative infinity to infinity. So we've satisfied that criteria. They are telling us that there is a solution to this, and that's a trivial solution. And that makes sense, because if we let y be 0, and we wanted to verify that, y prime would be 0, y double prime would be 0, and y triple prime would be 0. So if we plug those in for here, we're going to get 0 is equal to 0, which is a true statement. So because we have met the conditions for this theorem, we have continuous a sub n's here. A sub n minus 1 and so on. We have continuous functions in front of the y triple prime, y double prime, and so on. We're defined on an interval where not only these are continuous, but our initial value lives on that interval also. This guy's not 0 at that initial condition. Then we know that this has a solution, but this must be the only solution that satisfies that differential equation. We know that because the solution has to be unique, which means there can only be one solution that satisfies that. So that would be the only solution. Let's look at another one. Here we have a second order differential equation, and we have 2 initial conditions. Now we could go through and we could verify that this is the solution to that. We'll talk about how to solve that a little bit later in this chapter. So let's analyze the theorem with regards to this problem. So our constant here is 1. So y equals 1 would be continuous. Y equals negative 4 would be continuous. And then 12x is continuous. So this is continuous from negative infinity to infinity. If we look at the initial values, we were talking about initial values at 0. Well, 0 exists on this interval. Notice those are the x values we're plugging in. And this is in terms of x. So we've satisfied the conditions. That means that we have to have a unique solution for this differential equation. So if we know this is a solution, then because we know that we've satisfied the conditions for uniqueness, then this has to be the only solution for this differential equation with those initial conditions. So let's look at another one. Here we have a second order differential equation, and we have 2 initial conditions to satisfy that. They're telling us that this function satisfies the initial value problem. And it says that works for any value of c. So in other words, this is not unique. Okay, it's not unique because I have a variable in there where c can be a variety of things. So what happened with that theorem? What fell apart? Well, these functions are definitely continuous functions, right? Y equals x squared, that's a quadratic. Y equals negative 2x, that's a continuous function. Y equals 2, it's a continuous function. And then we have the function y equals 6, or we could think about function notation, f of x is equal to 6. All of those are continuous, so that's fine. We have initial conditions imposed at 0. That's fine, but think about what's going on here. There's a place where this guy's going to be equal to 0, and that's going to be equal to 0 at 0. And that's where our initial conditions are imposed. So that's where the problem actually is. That's where this theorem's kind of falling apart. Another way to think about this is that if you put this in standard form, remember standard form has a 1 in front of that highest order derivative, we would divide everything by x squared. And when we do that, we impose conditions on the problem, because now we can see there's definitely going to be an issue with x being equal to 0 because that's no longer defined there. But that's where our initial conditions are. They're at x equals 0. So that when that happens, we can't guarantee uniqueness of the solution any longer. So when we talk about initial value problems, we're talking about a problem that satisfies our criteria over here. Notice all of these are at the same x value. If I have an nth order derivative, I am substituting into y prime, y double prime, and so on, all the way up to the y to the nth minus first derivative. So, for instance, if I have a second order differential equation, we know we need two initial conditions. One of those conditions would happen at y, and one of those would happen at the first derivative. And the y value could be different, but the x value has to be the same. If we had a third order differential equation, then we would substitute into y. We would substitute into the first derivative. And then we would substitute into the second derivative. But we're always substituting in that x naught value, the same x value. If we have a boundary value problem, the initial conditions can look quite different. So let's say, just for simplicity's sake, we're looking at a second order differential equation, and they give us a boundary value problem. And that gives us something called boundary conditions. Boundary value problems don't necessarily have to follow that same format that we were talking about here, where we had to substitute into y. Let me use the second order up here, where we had to substitute into y and y prime, and we substituted the same x value. There's a variety of things that could happen here. Notice these initial conditions, they're both substituting into y. I'm substituting an a value and then a b value, so the x values are different. And there's actually a lot of combinations that could happen. We could substitute in a and b, both into the y value. Or we could substitute a into y prime and b into y. So still two different x values. Or we could substitute in a for y and b for y prime. So we've got that mix of different x values. Or we could just substitute things into the first derivative, an a value and a b value. So what's going to happen usually is that when you have boundary value problems, you'll be able to substitute these things, that information, into your solution and or the derivative of your solution if you have something like that. And that's going to give you a system of equations. And then you'll be able to solve that system of equations to try to figure out, do you have a solution for this? Sometimes the solutions may be unique. Sometimes you may not have a solution. Sometimes you may have a non-unique solution, or you may have many solutions for a boundary value problem. So the rules aren't the same for those as they would be for an initial condition problem. With an initial value problem, as long as you meet that criteria for that existence and uniqueness theorem, you're guaranteed to have a solution. That's not necessarily true with a boundary value problem. There's not a theorem that I'm aware of that would give you that would guarantee you uniqueness. So let's look at an example. If we look at this problem, this is the solution to that problem. Now let's impose some boundary value values on this, and let's see what's going to happen. Suppose we impose boundary values of x 0 is equal to 0 and x pi over 2 is equal to 0. Okay, notice these are going into that solution of x. Different x values are going in. 0 versus pi over 2. So let's see what's going to happen. So if we substitute in this one, we're going to have 0 equals c1 times cosine of 0 plus c2 times the sine of 4 times pi over 2, which is 2 pi. Well, we know sine of 2 pi is 0. Cosine of 2 pi is 1, so we get 0 is equal to c1. And now if we impose this guy, we get 0 is equal to c1 cosine of... hold on 1 minute. I think I did that incorrectly. I'm plugging 0 in. So this is c2 sine of 0. Sine of 0 is 0. So we have 0 is equal to c1. Cosine of 0 is 1. So 0 is equal to c1. Now let's impose this guy. And I'm actually going to write this over here. So we have 0 is equal to c1 cosine of 4 times pi over 2 is 2 pi. Plus c2 sine of 4 times pi over 2 is 2 pi again. Sine of 2 pi is 0. Cosine of 2 pi is 1. So we get 0 for c1 again. Okay, notice we ain't getting anything for c2. So what that means is that c2 can be anything. So then our solution is not unique. There's our solution curve that's going to go through this. That solves that differential equation, where c2 can be anything. So if we were to graph this, I'm just going to use Desmos to graph the solution. We have y equals c sine of 4x, and I added a slider for c, and I'm going through the point 0, 0, and pi over 2, 0. Those are both on that solution curve, x equals c2 sine of 4t. So you can see what that c value is doing. Everything's still going through those 2 points, the 0, 0, and the pi over 2, 0. It's just changing really the height of that, which is the amplitude of that curve. But if we were to change the initial conditions, or excuse me, the boundary conditions, so we have still x0 is equal to 0, but now we're changing that second one. A different point on that curve. Let's see what that's going to do to this initial value problem. So we know when we plug 0 in, we're going to get 0 is equal to c1. Okay, we did that up here. So I'm not going to work through that again, but let's plug the second one in. We have 0 is equal to c1 times cosine of, we have 4 times pi over 8, which is pi over 2, plus c2 sine of 4 times pi over 8, which is pi over 2. We know cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we get both c1 and c2 to be 0, which means that the solution is y equals 0 times cosine of 4t plus 0 times sine of 4t, which is just going to be y equals 0. So we get a unique solution. It's not a very interesting solution. It's just the x-axis. But it is a unique solution. So depending on the points that we go through, we may end up with a unique solution, or we may end up with an infinite number of solutions. In fact, let's suppose we impose a different set. So still this guy, which still means that 0 is equal to C1. But what happens if we change that second condition? If we change that second condition, we now have 0 equals C1 times cosine of 4 times pi over 2 is 2 pi. I'm just getting this at 1 there. Plus C2 sine of 4 times pi over 2 is 2 pi. Well, we know sine of 2 pi is 0. Cosine of 2 pi is 1. Check this out. But that can't happen. We can't have C1 to be 0 and 1. So we've got a contradiction here. And what that means is that we have no solution to that. There's no way this curve could go through those 2 points. We end up with 2 different C1 values. It's just not possible. So we have no solution. So depending on what initial values we impose on the differential equation, what boundary conditions we put on it, rather, will depend on whether or not we even have a solution to that differential equation.